This Tuesday, like tomorrow, we have a test over this last unit. Now, think well material, we started way back on 7.2 through all of chapter 8. So, and it essentially turns into basically two different types of problems. The applications that we saw in chapter 7 and the graphing and all the immense detail we talked about in chapter 8. We'll go break it down further, more details, but that's the basic idea on test 3 here, applications and graphing. And it's pretty much, a lot of it is dealing with the maximums and minimums. Graphing, we ran into maximums and minimums. The applications were pretty much all, not all, but the first couple sections weren't maximums and minimums, but most of them were. So, for the test, because these problems tend to be a little bit longer, as you noticed, there's only going to be 13 problems on the test. So I will go ahead and count each problem worth 5 points and then take a percentage at the end. So it's not going to be, you miss 8 points on the test, you get a 92. It's not going to work that way. You miss 8 points, you'll get probably an 86, 87, something like that. So a little bit more than 1% per point you miss. Yeah. But, okay. Well, first off, we looked at, 7.2, we saw some of the different applications. We started with the higher order derivatives. Second derivative, of course, we've been using the second derivative quite a bit in the graphing now. But in this section, we introduced the notation. Second derivative, third derivative, fourth derivative. So I may give you something, I may even give you the second derivative and have you calculate the fifth derivative, something like that. Let's just keep doing the derivative after the derivative of the derivative of the derivative of how many ever times you need to do that. So that's probably one of the easier problems on this test, but it's more, do you recognize the notation, what are you given, and how many times do you need to take the derivative to get to the end derivative. So, let's see. Then we also did the linearization. Now that's really just a fancy word for find the equation of the tangent line. So a lot of these, it's more formal definitions, formal terminology, but it comes down to using the equation of the tangent line. And within the linearization, or using the equation of the tangent line, we looked at some approximations. Approximate a certain value, like say the square root of 38. Well, square root of 38 is going to be an ugly number, but what's close to that would be a nice number. So square root of 36, we would say let x equal 36. Delta x would be what? 2. 38 minus 36, and then the derivative would be in there. The function itself would be the square root of x function. Take the derivative of that, and then make sure you get all the combinations correct. But there'll be, well, there's only 13 problems on the test, so there's not going to be a lot of anything. There may be one of these types of problems. There may be one of the higher order derivatives. Anything that I mention here, there's probably not going to be 3 or 4 of those types of problems, but maybe one of each of the things, and maybe none. There may be, I mean, I did have to cut back a lot on this because a lot of the problems are so long. Question? Okay, let's look at how we'd use the tangent line, or how we'd use the derivative to approximate the natural log of 2. First of all, the function we would be dealing with is simply natural log of x. And the, quote, nice number would be what? Okay. Let x equal 1. Natural log of 1 is just 0. So that'll, I'll go ahead and write it up, not that 0 will add anything to it, but just to see the form. So the natural log of 2 will be approximately, that squiggly equals is approximate, the natural log of 1 plus, man, my writing is bad today. It's not LU1, but LN1. Natural log of 1 plus the derivative of, we'd say derivative evaluated at 1 times the delta x. And that delta x would be the difference between the ugly value we're trying to find and the nice value. So delta x, in this case, would be the 2 minus 1. A lot of the problems we had, I think on the worksheet we used 1.5. So delta x would be 0.5 in that case. But in this case, delta x, nice little value of 1. Okay. Well, the most amount of work here will be your derivative. And that's not really a lot of work on this one. Derivative of natural log of x is?
1 over x.
And then evaluate the derivative at 1 at our nice value. And that's going to be what?
1.
Okay. So our approximation then, well, natural log of 1 is 0 plus f of primed of 1 times delta x. Natural log of 1 is approximately 1. Okay. Now, the exact value of natural log of 1 is 0.693. So that's pretty decent.
That's your answer, 1?
Yep. So this would be the process of approximating natural log of 2. Now, not a great approximation, but at least it gets us close. The smaller delta x is, the better the approximation would be. In the case of natural log, 1 is a fairly large delta x. We'd been working with mainly decimals, something between 0 and 1 for a delta x. So we got a little bit closer, but that's the process there. So, okay, questions? The other type of problem we looked at in that section was what's the linearization of the function at a certain number, and I think in their material they used like a equals 1. It just means the particular x value we're dealing with. And linearization, well, that again is just the equation of the tangent line. Now their formula looked a little bit different than what we think of when we say equation of the tangent line, but that's essentially what it is. Their approximation, this would be the f of a, or f of 1, plus f primed evaluated at a times, well, technically this would be the delta x that we talked about earlier, but x minus a, where a is 1. Now think about this. When we find the equation of a tangent line, the equation of a line in slope or in point slope form is this. Well, what we're actually doing is solving for y. Y would represent the f of x in this notation. We add y sub 1 to both sides, and we would get the equation y equals y sub 1 plus m times x minus x sub 1. Okay. Now that looks like a strange notation to us, but that's where they're getting their linearization or approximation of the function at a certain point. And for our purposes, y1 would be f of 1, f of a, so, or 0. And then the slope, well, like we saw in the approximation, derivative of natural log of x is 1 over x evaluated at 1. Slope would be 1. And then this is where the approximation is slightly different. Instead of just delta x, we have the x minus the a. So the linearization of the natural log of x is y equals x minus 1. Okay. Which happens again to be the equation of the tangent line to this curve at x equals 1. So a lot of different ways to say the same thing. Some things sound a little worse than they actually are, and that's definitely one of those occasions. Next up, Newton's method for approximating a zero of a function. And that one, well, the theory behind it gets a little confusing, but if you can remember the formula, once again, it's formula driven. Oops. The second x value is based on the first x value. The third x value is based on the second x value. So in general, we say x to the n plus 1 will equal x to the n minus f of x to the n over f primed of x to the n. Now this one, there's a lot of varied ways to remember what this is. For me, the way I have to remember this is the equation of the tangent line Now, the theory behind it is the y value that we are looking for next is the 0. We're looking for the x-intercept of our equation of the tangent line, and that would mean y equals 0. And we are looking for this next value of x. So if you can't quite remember what this formula is, maybe try to remember this. Solve for x, And, well, instead of multiplying the m through, first of all, divide both sides by m. And where y is 0, we'd have y sub 1 over m. Oh, and the negative. Don't forget that little dashed line. That's going to equal x minus x sub 1. And then add x sub 1 to both sides. Then, I mean, that's in more point form. That's the algebra form we look at. But x sub 1 is your x value. Y sub 1 is f of x sub 1. And your slope, m, would be what?
F prime.
F primed of x sub 1. So, for me, the hardest thing to remember about this formula is this fraction. What goes on top, what goes on the bottom. I always have to kind of re-derive the formula every time when I use it, but that'll help you remember. Oops. Okay, questions there? Now, the other main big problem here is what x value do we pick first? What should be our x of 1? And that's going to vary with the equation we deal with. Try to get x of 1 as close, make it an integer, 0, 1, 2, or -1, -2, one of those, the closest one to the actual 0. And to do that, you just kind of, sometimes you just kind of have to check, okay, f of 1 maybe 5, f of 0 maybe 8. Well, of those two, I would use 5, especially if f of 2 would be -7. Well, you know somewhere between 1 and 2 there is a 0. F of 1 gives us a positive y value, f of 2 gives us a negative. So either x of 1 equals 1 or x of 1 equals 2 would be a good choice. There's not one right choice. There are many good choices. Some are better than others. And then, of course, you get too far away and there's going to be some bad choices. So make sure you're at least close enough to the 0 to begin. Okay? So questions there?
Can you? I don't want you to go to an easy method, but just the first couple of step. Which
Okay.
Is, you set the equation equal to 0, right?
Well, by plugging in 0 for y, we get this formula. And so x sub 2, say, let's choose x of 1 equals 1. X of 2, we would calculate 1 minus f of 1 over f primed of 1. And then whatever our function happens to be. And then calculate that. Then turn around and use this value here. So x sub 3 would equal x sub 2 minus f of x sub 2 over f primed of x sub 2. And it's called reiterate. So kind of figuring out, the main thing there again is remembering the formula. And then I will instruct you to continue the process until two successive approximations differ by some amount. Probably the 0.001 as I used on the worksheet. So just to make sure we get close enough. But it's probably, I won't give you something that you'd have to do 10 times, maybe 3, maybe 4 times, but not ridiculous amount. Unless you're way off at the beginning, then it might take that long. But if you get somewhat close at the beginning, should be probably within 3, 4, 5 times. Okay? Then we got into a major topic of optimization. We saw several worksheets on it, several different types of problems, but all were essentially the same approach. We want to, optimization, either maximize something or minimize something. And to do that, most of the time we had some description and maybe maximizing area based on a restriction on perimeter or something like that. The field with a fence going around the edge and then one down the middle, a certain amount of fence, given amount of, I call it perimeter, but technically it's not really perimeter with the one going down the middle. But given the amount of fence, how big of an area, maximize the area that could be enclosed. So one piece of information will give you a relationship between two quantities. The amount of fence will tell you the relationship between length and width, or X and Y, whatever you draw a picture. A lot of these you can draw a picture and figure that out. And then area, length times width, well, we want to change that into a function of just one variable. So X might equal 2Y minus 100 over 3 or something like that. But plug that in, and then you got your X times whatever the Y value is in terms of X. So lots and lots of different possible types of problems. We looked at 4 different worksheets on those types of problems, so go back to that. But main thing, we're looking for the critical numbers, critical points. This is where the maximums and minimums will occur, and then plug in the value. Sometimes the question was, what are the dimensions? So you have to go back and figure out what would the length be, what would the width be. Sometimes it was, what is the maximum area? So you got to really be careful with what question is given to what the problem will look like, or what the answer will look like. Okay. And on those, I think I've mentioned this before, but any of the common area, or as we move into 3 dimensions, the common volume formulas, you need to know those. But if it's like the volume of a cone, I would give that to you. I'll give you the more obscure formulas, and there won't be the octagon. Don't worry about that one. Again, some of these are better homework problems than there are test problems, so I like that one. But volume of a box, you guys better know the volume of a box. Length times width times height. Surface area of a box, well, it's the area of the rectangles that make up the box. Now, cylinder, you may have that. Volume of a cylinder.
It's 1/3.
Cylinder. 1/3 is your cone.
Oh, the cone.
And like I said, I'll give you that one. But volume of a cylinder. Pi r squared h. It's the circle area of the base times the height.
Pi r squared is it's not the circumference.
It's the area of a circle, and then times the height. So that one's probably the most obscure of the ones I think you should know, so make sure you know that. And then the surface area of a cylinder, this one's also not quite as familiar, but depending, is it closed? If it's closed, it has a top and a bottom. If it's open, it just has one. So we'll say closed. So top and bottom, 2 circles. And then what we call the lateral surface area, the curved side would be what? And that's actually the 2 pi r h. You can think of that as cut down one side and unroll it. What shape do you get?
Square.
A rectangle.
Yeah.
Could be a square, but a rectangle. And the length of it is going to be the circumference of the circle.
Yeah, because you close it and
And then the width of it would be the height of the cylinder. So again, some things, if you can't remember exactly the formula, you can at least think about how to develop it. Now, some of the specifics, I mentioned the area and certain amount of fence. Maybe it's the creating a box from a flat piece of cardboard and cutting out the corners, flipping up the sides. We did several of those. And we did several volumes, maximize volume given a certain surface area, or minimize surface area given a certain volume. So it just depends what we're given. Same basic process. And then the sum of perimeters and all of those, minimize the areas or something like that. But create your function that you're trying to maximize and minimize. Then look at the relationship between given the sum of the perimeters or something like that. Then plug that into the function you're trying to maximize or minimize. Somehow you should be able to create a function of just one variable. Then you're ready to take the derivative and set the derivative equal to 0 and solve. So, questions about optimization? Another fun type of problem, the related rates. And again, we looked at lots of different ones there. Once again, the main thing, create an equation that relates all of the parts. Some of the parts may be constant no matter what time, but other parts are variables. Make sure you don't just plug in all the constants and then take the derivative, because you'll get 0 equals 0. But like the ladder sliding down the edge of a building, well, this is going to vary, this is going to vary, but the ladder will be a constant. Maybe it's a 20-foot ladder. Okay. So also keep in mind the rate at which the bottom of the ladder is sliding along the ground. That's going to be your dx by dt. The rate at which the top of the ladder is sliding down the building, that would be dy by dt. What do we know about either the dx by dt or the dy by dt? What could we say about dx by dt? Okay, that rate of change will be positive because x is getting bigger.
Mm.
So then what would dy by dt be?
Negative.
Okay, dy by dt would be negative because sliding down, y is getting smaller. Y is decreasing. Now we got a little more into that as we looked at the graphing,
So
but that's the same idea. Negative derivative means that value is decreasing. Yeah.
so when we do the equation, which is actually going to be the Pythagorean theorem,
Mm-hmm.
for dy dt, you're going to plug in a...
Well, one of these values would be given to us.
Okay.
So like the ladder is sliding down the side of the building at 2 feet per second. That would be cruising. Maybe 2 inch per second. That would be a little. But that would mean dy by dt would equal -2. Got to remember,
So you plug
even
in-
though the
you're plugging in
description,
negative,
right, the description is not specifically saying -2, but it's sliding down at a rate of 2 feet per second. We need to remember that's a -2 for dy by dt. So, and what would dx by dt be? What would the rate of the ladder sliding along the ground? So, we'd first have to do this. And we would know this. We're looking for this. Now, we would need a little more information. The question would say, how fast is the ladder sliding along the ground when the base is 6 feet from the edge of the building? Well, that's saying essentially dx by dt equals what when x equals 6? Well, we'd be able to plug 6 in for x. We have the -2 for dy by dt. What about y?
You can just plug it in Pythagorean.
Okay, go back to this. When x is 6, we'd be able to find y. Y is not going to be a real nice number here, but hopefully the numbers will work a little better.
Yeah.
But that you'd be able to calculate what y is based on the Pythagorean theorem. So that's what you'll find with any of these related rates. Key point here, make sure you get a relation between your variables, an equation of some sort. And most of the time, two of the variables will be two of the parts will be variables. One part may be a constant, but there were some problems where all three parts were variables. Okay. When a couple of cars left the same point, one going north and one going east, well, the distance between the two cars, all three of the portions would be variables here. So in that case, we won't have our nice little derivative of a constant equals 0. But procedural wise, it's same basic steps. It's all those details to keep track of. Okay? So there's your related rates. Lots of different types of problems, but again, same basic steps to go through those. Now on chapter 8 in the Think Well material, this kind of brought us back to graphing functions in 2 dimensions, but it's still using maximums and minimums. Critical points, find the maximum value, find the minimum value. Graphing wise, that's essentially where the graph turns around. So a lot of the same procedures, although they represent kind of a different idea when you're talking graphing. But We did lots and lots of things, lots of particular details on the graphing parts. And then, of course, the last few worksheets were graph in detail and all the stuff. On the test, I'm not going to have one problem that says graph this in detail showing this and this and this and this and this. Okay. There will be problems that say show where the function is increasing and decreasing. But that will be one problem in itself, not one part of a huge problem. So, yeah.
So when you do that, like we're showing it increasing, do you want it in like x is greater than less than form or like the time?
Intervals?
I'm not real picky on that. Where is a function increasing and decreasing? If you want to put x is less than 2, that's fine. Or if you want to put negative infinity to 2, that's fine. So, yeah. I'm not going to be picky on the form. Just make sure it's right. So, but graphing, we looked at, well, I guess, first of all, critical points. One problem may be find all the critical points. Maybe. Might be a little bit more involved than that. Then one of the first things we looked at were absolute maximums and minimums, extreme values, extrema, whatever term you want to use there, over an interval. Now, some of these would have both a maximum and a minimum. If it's a closed interval, we're guaranteed that it will have both. Now, the maximum and minimum, the absolute maximum, could occur at a critical point or at an endpoint. So make sure and check your endpoints as well and then compare. Sometimes the critical points are not inside the interval we're looking at either. So make sure and get only the critical points inside that interval. So that was from our first worksheet with the graphing. Then we got real specific with the increasing and decreasing intervals of increasing and decreasing. And again, whether it's interval notation or your inequality notation, I don't care. Then local maximums and minimums using the first derivative test. Is it increasing and then decreasing? If so, that critical point would be a maximum, or is it decreasing then
increasing? Are we going to have to plug in the
increasing?
critical point into the f of x function, well, into the real function to find like the y value?
Yes. If you're asked to find the maximums and minimums, that's not just the x value, but that's the point.
Okay.
So that's where you plug the x value, your critical point, into your function value to get the y.
Okay.
Not f prime, but into f of x to get the y value. Yep. Yeah, they're not real clear on
Okay.
their problems. Yes,
So
Kate.
you have the interval, and you have say you have like a parabola, and so the endpoint of that parabola on the interval, that'd be the max, right?
Yes.
Like, even if it isn't.
If you're looking at a function over a certain interval, then the maximum would occur at an endpoint.
So like, what if it wasn't bracketed and it can't be equal to?
Okay, then there's no maximum in that
So
case.
there's just none.
Yeah. Yeah, if the interval is not closed, if it's got the parentheses around it, then that means up to but not equal to those endpoints. Then we may have a minimum but not a maximum. Or vice versa, we may have a maximum but not a minimum. Okay? Increasing and decreasing dealt with the first derivative, concavity. concave up, concave down deals with what?
Second.
Okay, second derivative. So, second derivative being positive, that would be concave up. Second derivative being negative, that's concave down. Okay. So again, one problem will be what is the concavity of this function? So not one part of a huge problem like we've done with the graphs. Yes,
And
James?
you set the second derivative to 0 to find the inflection points.
Right. Set the second derivative equal to 0 to find the inflection points,
Like
or
the whole
possible
thing?
inflection points.
The whole
Yep,
thing?
the second derivative equal to 0, the whole second derivative, and then solve. And then, let's say we get x equals -1 and x equals 2 as possible inflection points. Then you have to test the intervals to see, well, at the left of -1, is it concave up, or is the second derivative positive, negative? Okay. Then in between, is it positive or negative? Well, if both are positive, then at -1, then there's no inflection point there. It's one of those kind of strange graphs.
I thought you said
But-
the
But if it goes from positive to negative, then yeah, there's an inflection point there. So that's going to be the key part to those. Let's see. A lot of the final worksheets we did were graph these in detail. Well, again, I'm not going to have those particular problems. But one more particular type of problem that we'll be looking at, asymptotes. Find the asymptotes. Now these could be vertical. Well, if I say just find the asymptotes, then it will be find all of them. Vertical asymptotes, horizontal asymptotes, or oblique asymptotes. We're not going to have both horizontal and oblique. It will be one or the other. And that quick check on that is based on the exponents. Higher degree in the numerator than the denominator will have oblique. But if they're the same or less in the numerator, then it's going to be a horizontal. Okay? Okay. Question.